definition for a polynomial function of degree n. When you look at something like this, what happens? What happens? You get scared, yes. However, you have seen lots of polynomial functions before. Just, Jesse, I'm going to get you there, okay? Okay, there you go. All right, so, but when you see something like this, it's like, oh my God, life is so complicated. Part of it is, it's really hard to write something generally that covers every possible polynomial in the whole wide world. That's why it looks so complicated. If you just look down to number 2, for example, f of x equals 11x cubed minus 6x squared plus 1x plus 3. Does that scare you? No. Why not? It's filled in. In other words, instead of seeing a sub n, you see the number 11. And instead of seeing that exponent n, you see the exponent 3. Okay, so it's a specific polynomial. So let's not freak out about this definition. Let's just try to understand it briefly. You'll have a lot of practice with understanding the vocabulary in your first class activity today. First of all, if we look at the function in number 11, notice that the highest power you see as you look along the right side, the expression along the right side, the highest power you see is 3. So if you were to say, okay, this n here is 3, because that's the highest power. That's what this n would be right there. Okay, it would be 3, because it's the highest power you see. So we call this a third degree polynomial. And for a couple of our polynomials, we have names like linear, quadratic, and we call this a cubic polynomial. Quartic would be 4, quintic would be 5, sextic would be 6, and then we got to go into our ratings, right? Okay. No laughs even, no smiles. Boy, I don't know, it must be the rain, huh? All right, so that's, since we don't know what degree our polynomial has to be, this is how we represent it, a to the n. Now, each one of these terms, remember, terms are the adding and subtracting parts of an expression. This coefficient, because of its little subscript here of n, tells you I belong to x to the n power. That's just a label. It's an address. So in this particular example, a sub 3 would equal 11. It says, here's where I live. I live with the exponent that's the third degree. All right. Now, after the third degree, I could have 3 more terms like you see here, or I could have nothing. I could just be f of x equals 11x cubed, and that's me. Okay? So what are the possibilities once you know your highest degree? Well, your next term could be a degree 1 less than that, right? That's what this says. I would now be x squared. I'm 1 less. 2 is 3 take away 1. And then, you know, this can go on, and at some point you have to put specific numbers in to show how it ends. You also have a possibility as you get to the end to have an x to the first power. And that's what you see right here. And then finally, you have what's called the constant term. Why does this say a sub 0? Why does it say a sub 0? Because if you put a variable to a power beside it, remember we said the power and the subscript here, the superscript and the subscript have to match. X to the 0 is defined to be what number? X to the 0. You answered the question, Jesse, a sub 0 is 3, and I agree with that. But what is x to the 0 equal? 1. Any number raised to the 0 power except for 0 is 1. So we don't bother putting in x to the 0 because it's just 1, and that's why we just have a constant term there, a sub 0. There's no variable attached to it, but you could if you wanted to, just so you could see the progression from n all the way down to 0, right? So polynomials always look like this. It's a finite sum. In other words, you can count the number of terms. It could be this long, or it could just be a constant like this. Okay? The nice thing about polynomials versus other functions that we've looked at or will look at is that every single power is non-negative. Non-negative means a non-negative integer. 0, 1, 2, 3, 4, 5, 6, like that. Beautiful. There's no fractions that you have to deal with. There's no denominators you have to worry about. So polynomials are really kind of fun functions to graph. Once you learn some of the main ideas, which we're going to cover today, you can do a relatively quick sketch of a polynomial function. Okay? So in terms of language, all of these an minus 1, a2, a1, a sub 0, those are called coefficients. The leading coefficient goes with the term that has the highest degree. It's the leader of the pack. Okay? So let's just practice some of this on this function right here. I'm going to actually erase that pink because it's a little too dark for me. So let's make it yellow highlighter right here. Okay, so here's our function. We call this a cubic function. Notice it's degree 3, but if it has all possible terms from 3 down to 0, it has 4 terms. Okay, and each term has a name here. This is called the cubic term, 11x cubed. Negative 6x squared is the quadratic, linear, constant. Still degree 3 because that's the highest power but there's 4 terms in this case. We could have 3, we could have 2, we could have 1. Okay, but the most it could have is 4. All right. Identify the degree, the leading coefficient, the leading term, the constant term, and the domain of the polynomial function. So let's fill this in. Jesse's already helped us. The degree here is n equals 3. You could just put a 3 if you want. I was just showing you where you find it. It's the, in our definition, it's the value of n. The leading coefficient, what's the leading coefficient here? $11, yep, because it's the coefficient that goes with your highest degree. So in this case, 3 is my highest degree, my highest power. My highest power is called the degree, and its coefficient is a sub 3 in this case. So a sub 3 would equal 11 because it has the same little address as the exponent. Now put it all together and tell me the leading term, Cyrus. Yep. And what's the constant term here? Clay, can you help me with that? X would be the linear term because it would have 1 as the power. The constant is a sub 0. It has no x attached to it. So which one do you think it would be? Okay, anybody want to help out? 3, right. It's the last term, and it's not always the last term because it's not always in descending order, but in this case, it goes from 3, 2, 1 down to x equals x to the 0 power. And so even though we don't write x to the 0 power, we just see the constant term there. So that's 3. It's the only term here that is constant. Everything else changes because it has a variable attached to it, right? If I put in a number like, if I find f of 2, each of those terms changes except for 3. 3 is always 3. It's constant. And the nice thing about polynomials is that the domain for polynomial is all real numbers. You never have to worry about zeros in the denominator. Why? Because you can't have an exponent to a negative power. You don't have to worry about square roots and fourth roots because you never have fractional exponents. So these polynomial functions always have all real numbers for the domain. You never really have to think about the domain. All right, graphically, what do they look like? Graphically, they're nice, smooth, and I didn't use the word continuous because you really don't deal with the idea of continuity until calculus. But I could have said these graphs are smooth, continuous curves that do not have any breaks or gaps in them, and they have no sharp corners. Like I could just put my pen on the paper and trace it just like I'm doing now, like this, without ever lifting it off the paper. So if we looked at the graphs below, I want you at your seats now, and I'm not even going to come around and look, just circle the graphs that you think represent the polynomial functions. Smooth, continuous curves, no corners and no breaks. And then we'll compare what we found. Okay, so anybody want to volunteer what they found for a polynomial function, what they circled? Yeah, Lorenzio? The first one, yeah, that's definitely a polynomial function. You don't see any gaps here, you don't see any sharp corners, just a nice, smooth, continuous curve. Are there any other polynomial functions here? James? The last one. Yep. Those are the only two polynomials. Because this one is what? A transformation of absolute value, right? So that has a sharp corner. So that's not a polynomial. And this one has a huge gap. That's not a polynomial. Okay? All right, so we're going to play around with this function today, a little bit here on this page, and then a little bit more detail on the next page. So here's a polynomial function that's a little more complicated than anything you've drawn before. But at the end of today, you're really going to be able to see how you could come up with the equation for this, believe it or not. It's amazing. We're going to tie together all the stuff that we've learned so far in the class to come up with this equation. Now, today I'm going to be talking about stuff that you already know, familiar terms like x-intercepts, zeros of the function, your turning points, those are like relative minima, relative maximum, right? Those are relative extrema. Now, we've talked about all these ideas. We're going to put those ideas together with some new ideas, which is behavior near a zero. So on this graph, there are 3 zeros. Those are the 3 values of x that make your output 0. So we know that f of -3 is going to give us a 0. We know that f of -1 is going to give us a 0. And we know that f of 2 is going to give us a 0. So that's 3 solutions to this equation. What values of x make this 0? You're solving an equation when you answer that question. So it should either be in this format, x equals, x equals, x equals, or this format, solution set. No parentheses, we're not giving coordinates, we're not giving intervals. So when you find the 0 of a function, you're solving that equation for x. Now, yes, all of these ideas translate to points on the graph that you know in your heart are called x-intercepts. But if I ask you for the zeros, you don't give me coordinates for the x-intercepts. You tell me the value of x that makes the function 0. But that's its visual representation, the x-intercept. All right, so one of the things we're going to talk about today is the behavior. That's kind of a strange thing. It's like going to a therapist, right? And you're talking about the behavior of your child or something, you know. You're talking about what does the function do near those 3 points? What does it mean to talk about its behavior? We're going to talk about that in a lot of detail today. The other idea has to do with the end behavior. Look at what I'm doing right now, right? Touchdown. Wow. The end behavior says, what does the graph do as x increases without bound, as x moves towards positive infinity, and as x moves towards negative infinity? And in this situation, the graph rises on the right and it rises on the left. I say both arms are up, okay? So that's end behavior. If you look at x cubed, the parent function that you graphed on the first question on your project, remember, my shoulders are acting like that, flattening out, and my head's like the origin. It looked like this, right? It had the right arm up as x went to positive infinity, the graph grew without bound, and as x went to negative infinity, it decreased without bound. So these polynomial functions are either going to be like this, like this, like this, or like that. Right? There's only two positions for each arm. So we're going to talk about all of that on the next page. And how do we determine, how do we talk about behavior? What words do we use? What language? Let's quickly go to the next page. All right. So there's a test that your book refers to as the leading coefficient test, and you're going to have lots of practice with the leading coefficient test on your homework, for those of you who do homework. And as x increases or decreases without bound, that's whether your graph rises or falls in each direction, whether it increases without bound or decreases without bound. So there's always a way to tell as x approaches positive and negative infinity. It's rising or falling. So where do we focus? Well, we always focus right here on a sub n. The leading coefficient is where the story is. And how do you remember this? Everything we talk about today, if you have an image in your head, you don't have to memorize stuff. If you keep two parent functions in your head, let's say this parent function and this parent function. We're all very familiar with those two functions. Straight line through the origin, this is called the identity function because x and y look exactly the same, and your basic parabola. Right? We all know what those look like. So if I happen to change, let's call this h of x, I change the leading coefficient on that. I go from a line that has a positive slope, my right arm up, my left arm down, my right arm rising, my left arm falling, to a negative slope, left arm up, right arm down. Right? So that's one image to keep in your head. I suppose I don't want you to think of me as walking around like this all the time, right? I look kind of odd, odd. Look at the power, odd power, okay? Then you have x squared, happy parabola, yes. So the coefficient there is positive. And then if we move to a negative leading coefficient, I'm droopy sad. That's all you have to remember because there's your two categories right there. Is your highest power odd? And if you're odd, you're walking around like this. And if you're even, you're walking around like this. Hey, nobody would think you're weird going like that, right? We all kind of do this kind of thing. All right. So notice all these pictures have lots of humps and valleys because as these powers grow, we can get lots more humps and valleys. But every polynomial will fall into a category where the degree is either even or odd. So it has to act like one of these four pictures. Only choice. Now, do you have to memorize these pictures? No. You just have to think about your line with a positive slope and negative slope, which is odd, and your baby parabola with a positive and negative coefficient, leading coefficient. That's it. And everything else falls from that. So n is odd. Think about this. You could have, this is a cubic function. If I were to find the equation for this function, it would be some positive number times x cubed with a bunch of stuff after it. How do I know the number's positive? Because my right arm is rising. Every time my right arm rises, I'm positive. My leading coefficient is positive. If n is odd and my right arm is drooping and falling, I'm a negative leading coefficient. So if you're an odd degree and your leading coefficient's positive, your right arm's up, your left arm's down, and vice versa. Notice with odd functions, your arms are always going, your end behaviors in different directions, right? I look like one of those flag people out there in the highway, right? When you have an even degree, just think of parabola. You're always going in the same direction as x increases and decreases without bound. You're happy or you're sad. And when the leading coefficient's positive, you're like this, and when it's negative, you're like this. So this is why they call it the leading coefficient test, because it's that leading coefficient that determines the behavior. On their far right-hand side, if n is odd, your far right side goes up and your left side goes down. If n is even, they're in the same direction, up or down. So we're going to come back to this polynomial we're just looking at in a minute. This is going to be sort of a good 15 minutes of me talking with you. So I hope you drank some coffee. We don't usually spend this long talking, but there's a lot going on here that I want to make sure you understand. So here's this polynomial right here. Look, that doesn't look like the polynomial at the beginning. I want to write this out for you for a second. So help me if I forget it. F of x equals, what was it? X plus 3, x minus 2 squared. All right. Wow. So this is what I'm getting at with the question Jesse just asked, so that you can see the difference. So Jesse said, can I put this in ascending or descending order? Well, that's a good question. And it was kind of what I was getting at, or going. I actually paid Jesse to ask that question today. What's the degree of this polynomial? And that's what I thought you would say. 3, 4, 6. I've heard 3 answers. 3, 4, 6, and wait. Okay, I'll wait. Okay. Wait is your favorite number. All right. Oh yeah, it is 6, Jesse says. So I've heard 2 6s. I've heard a couple of 3s. Oh, I hear another 6. 2 more 6s. What? What's going on? You said look for the highest power. Highest power I say is 3. What's going on? Have I like just turned the world upside down and totally like contradicted what I said at the beginning? Kind of, yeah. Not really. But it kind of looks like I have. Look at the definition of the polynomial function that I gave you in number 1. What are all the operations in between there, Dylan, on number 1? Huh? In number 1, what's the operation between all of them? Addition. So it could be addition or subtraction depending on whether the coefficient's positive or negative. That's what makes a term. It's a finite sum of terms. There's addition or subtraction between them. What's between those 3 things? As I fall over the board, what's the operation? Multiplication. This is factored form, folks. So it's going to be still many terms, but you'd have to multiply this all out. Frankly, I don't want to do that. I could very quickly. Well, fairly quickly. Right? But all I need to think about is if I multiplied, say, this out, x minus 2 times x minus 2, I would get an x squared in there. Does everybody agree with that? I'd get x squared minus 4x plus 4. That's what I'd get. If I multiplied this out, I'd get x cubed plus x squared plus x plus 1. And there's no multiplying out to do here. It's just x plus 3. So at some point, if I put all those factors out and I squared them and cubed them, this x would have to multiply the x squared from here, which would give me x cubed, and then that x cubed would have to multiply the x cubed from there, which would give me x 6. So the very first term that I would have if I multiplied all that out would be x to the 6th. And since there's a 1 here, there'd be a 1 in front there. So the leading coefficient's 1 here. Right? But I don't want to have to think that hard. So, can anybody see the relationship between these 3 numbers in that degree? Just add them up, right? So if it's in completely factored form, You just add these exponents to get your degree. Now, believe it or not, the leading coefficient test tells me something about the end behavior here. 6th degree, I'm even, woohoo! My leading coefficient is 1, woohoo! I'm a happy polynomial. Notice the end behavior looks just like I do right now. Both arms are up. This rises as x decreases to infinity, and the graph rises as x increases. So the first thing you could do if I gave you this, the first thing you could do would be to put 2 arrows up there. You know, that's the end behavior. Now, how do I make the relationship between these x-intercepts, which are the zeros, to the behavior that's going on right there? That's the whole, like almost the juiciest part of polynomial functions. It's happening right here in number 6. Okay? So we talk about the behavior of the graph at the x-intercept by examining the multiplicities. That's a brand new term, multiplicities. Haven't seen that before. The multiplicities of the zeros being x negative 3, x negative 1, and 2. So let's start with negative 3, 0. Let's look at its behavior. And before we do this, I just had this idea between the first class and the second class. I didn't even do this in the first class. Okay, here's f of x equals x. Remember this slider thing? I was like, oh, I could use the slider today. So we're going to focus on this 0 right here, because the only 0 of this function is at the origin, right? 0, 0. So when x is to the first power, what does this line do near that value right there? It crosses over, right? It goes from being negative to positive, crosses right through. Let's stick with the odd numbers for a minute. What would be the next odd degree? 3. So let me go up to 3 now. Now what am I doing? Oh, I've decided to flatten out a little bit, like my shoulders here, right? I'm flattening out as I approach that 0, and I'm a little flatter. But notice my behavior is very similar. I'm going through 0. I'm going from negative to positive. What about x to the 5th? Anybody have any prediction about what's going to happen to this graph? How it's going to look? It's all right if you're not right. It's all right to say something and who cares? Yeah, what would x to the 5th look like? You think it's going to be a line like x to the first power? Oh, well, it still has the same leading coefficient. I haven't changed that. So I'm still going to rise and fall here. I'm not changing my end behavior at all. Yeah, Dylan? Oh, you think it's going to have more hills and valleys than it does? This doesn't have any hills and valley. This function is always increasing. Even though right in here you can't see it, it's always increasing. Just like x to the first is always increasing, yes? So I'm going from negative to positive. Let's go up to 5. You can't really know this, folks, if you haven't played with this before. So it's okay if you don't know the answer, or even if your answer wasn't correct. It's all right. It's fine. We're just playing here, trying to learn. X to the 5th. What happened between x to the 3rd and x to the 5th? They kind of look the same, don't they? It just, yeah, that flatter part got wider, right? So what do you think x to the 7th would look like? It's just even wider and wider, and it's only because of this axis. If I made these axes, the y-axis here, in increments of like 100th or a 10th, you would be able to see the space between the curve and the x-axis, right? All right, but what's critical here, folks, is at that 0, whether it was x to the 1st, x to the 3rd, or x to the 5th, my function changed signs. It crossed right through that x-axis. Yeah? Now, depending on the power, when I say crosses right through, it crossed right through, really right through, when it was just x to the first. It flattened out a teeny bit when it was x cubed, and it flattened out even more when I was x to the fifth. But the point is, my function changed sign there from being below the x-axis to above it. Now I don't have my eraser. Duh. So now I've got to, how am I going to undo this? I don't have the, let's see if I can get this eraser here. And I don't know, I'm going to try. Yeah. Let's see. Maybe I can just move this off to the side here or something. Oh, I can move all these over. There we go. Oh, that's going to be a, there we go. Whee! All right. Let me just get each of these. Oh, there we go. All right. Now let's talk about the degree being even. So let's make this 2, because that's our parent function, x squared. Here's 2. So do I change sign as I come down to this 0? What was I to the left of this 0? Above the x-axis? What am I to the right of the 0? Above the right x-axis? Did I change sign? No. I bounced straight off of that 0, didn't I? Boom, right back up in the same direction. What do you think is going to happen to this curve when I make it x to the 4th power? No more terms added, nothing else, just I made the degree higher. Think about what happened when you went from the 1st degree to the 3rd degree to the 5th degree. Its bottom is going to get wider, right? It's going to get flatter. So I go up to the 4th degree, see how I get flat? And I don't have the 6th degree on here. The 6th degree would even be flatter. All right, so that's what we're talking about when we talk about the behavior near the 0. What we're going to be asking is, does my graph go through the x-axis? Does it go straight through like a line? Does it flatten out a little bit? But the point is, if it goes right through, the sign changes, you have to be odd. If I bounce in either direction, up or down, I've got to be a square or a 4th power or a 6th power. So here, we look at the graph at the x-intercept, and the graph passes directly through. And so when you're looking at this, you kind of remember the little magic pen idea here, right here. You're going to just focus on that neighborhood near the behavior near that 0. And that looks just like a line going through there. So that means it's odd. The multiplicity is odd. Okay, that's what we're talking about right now, multiplicity. Odd or even, that's all we want to determine first. If it goes through, you're odd. Right, let's look at this one for a minute. Does that go through? It bounces, right? That means you're even. Your multiplicity is even though you haven't seen yet what the multiplicity is. What about this one? Do you go through at -1, change sign, or do you bounce? Go through. That's odd, but does that look like x to the 1st? No, it looks like x to the 3rd, right? Because it flattens out near that -1. All right. So, always odd if it goes through. Yep. If you change the sign, yes. All right, so let's take a look at -3, 0. -3, 0 are the coordinates for the x-intercept. The 0 is -3, which means the factor is x plus 3. Because when I put a -3 in here, I get a 0. So that means my factor, when I completely factor my polynomial, that's going to be what one of the factors looks like. Near this 0, the behavior is I change sign. You could say I change sign, or I go straight through like a line. Whatever you want to say. I cross the x-axis. However it makes sense to you. I'm not going to tell you what makes sense to you. You just pick what works for you. Okay? Since there's only a single factor of x plus 3, look up here. There's only a single factor in this polynomial of x plus 3. Its degree, its exponent there is 1. We say It has a single zero, -3, and has a multiplicity of 1. So whatever your exponent is the multiplicity. When it's in factored form, folks, everything, think about multiplicity, multiply, factors, factors, factors. You can't tell a darn thing about multiplicities if it's not in factored form. All right, so the multiplicity of the 0, you could say, is 1. And you could actually say it's odd, but when I ask you to state the multiplicity on your project, I want the number. You could first say odd to get a sense of whether it's going to be 135, but I'm looking at what the exact multiplicity is. So let's do this same behavior now for the other two zeros. Let's go to 2, 0 now. So that's the x-intercept 2, 0. What's the 0 of the function? X equals what? 2. And if x equals 2, then I know my factor looks like this, x minus 2. Because my factors always have this form, x minus whatever your 0 is. This is your 0. It's always a subtraction. So when your 0 is negative, the subtraction becomes addition. What's the behavior near 2? What's it do? It bounces. Yes, it doesn't change sign. It bounces. This has a multiplicity of 2 right here. It's even. It's got to be even. And since it doesn't really get flat around 2, it looks like a parabola or a quadratic there. And then our final one, see if you can fill in the next row for the -1, 0. This one right here. See if you can fill that row in all the way across. Someone want to help me? We have 1, 2, 3, 4, 5 columns to fill in. Anybody want to help me with any of the columns at all? Jesse, which one you want to pick? Read the column heading here. Which one you want to do? What is the x-intercept? Yep. Okay. Someone else for one of the other ones? James? X equals -1. Was someone else going to say something, Paul? X plus 1 is the factor. Woohoo. Notice, you know a 0, you know a factor. You know a 0, you know a factor. You know a factor, you know a 0. Behavior or multiplicity? Anybody else? Yeah. Yep. 3, absolutely. And the behavior, cross through or bounce? Oh, Dylan? Crosses. Okay. Okay. So the final thing here is how do we determine the degree? We've already done that. When it's in completely factored form, you add the exponents. So the degree here is 6 degree. All right. Now we're ready to graph any polynomial function. Can you believe it? Anything. So let's take a look at the next page. All right. Now that we've explored the ideas of end behavior, zeros and their multiplicities for polynomial functions, we're ready to get a quick sketch. It's not going to be exact, folks. It's just real quick, okay? So the first thing we do is we figure out the end behavior. That's the first thing we do to graph. We want to know, does this function rise and fall in different directions or in the same direction? So you go to the leading term and look at the leading coefficient. The leading coefficient here is 1. It's positive. That tells me my right arm is up in the air. That's the first thing I determine. What is my right arm doing? Here it is. It's up in the air because my leading coefficient is positive. Now I just have to figure out about going in the other direction towards -infinity. What's my graph doing at that end of the graph? What's my left arm doing? Well, that's determined by whether I'm an odd degree or an even degree. And since this is in polynomial form, I search out the highest degree, which is 5. It's odd. Oh, my left arm's going to go in the opposite direction, which is down. So this is how I start my graph, just like that. There I am. Now I just got to fill in the in-between behavior, right? No, it's not a bad idea here. All right, let's see. Now, the next important thing after all the time we spent, where are your zeros? Where are your zeros? Which corresponds on the graph to where are your x-intercepts? The only way you can figure them out is to set your function equal to 0, since that's what you're finding when the output is 0. And then you have to factor that polynomial. So before I even start, what's the y-intercept here? What's the y-intercept? The coordinates of the y-intercept. Not a hard question, folks. 0, 0. Look at your constant term here. You don't have one. You could put plus 0 on the end of that. You don't change it. Your constant term is always the value of your y-intercept, the y value, right? 0, 0. So if you have 0, 0 as a y-intercept and an x-intercept, in this case, both, you know you have to have a greatest common factor, because the only way to have x being a 0 is the factor has to look like that with some power up here. I don't care which power it is, which means it's just x to some power. That tells you to begin factoring, you've got to look for that greatest common factor first. That's what the greatest common, that's how it translates to a graph. So greatest common factor, if you look across this expression right here, what's the greatest common factor? Not 3x, x cubed. And I think that's what you meant, Jesse, right? Yeah, okay, so let's pull out the x cubed. What's going to be the highest power I see inside this parenthesis if I'm already taking 3 factors of x out? How many factors of x will be left inside, and the highest number of them if we had a 5 here? 2, right? It's got to be a quadratic expression inside. X squared minus 6x plus 9. All right. So I've done my first step in factoring. I think you could all factor the next one, but again, let me give you a little hint here, whether you need it or not, how you start to notice these things. Notice x squared is a perfect square, so is it 9. What do I square to get x? X. I mean, what do I square to get x squared? X. What do I square to get 9? 3. 3x doubled is 6x. So this is a perfect square trinomial. So to factor this, I just say x minus 3, and I square that baby. Remember, you always get that middle term that's double. All right, now that I've done that, I've completely factored it. No problem. And now I set each factor equal to 0. Well, if you wanted to, you could call x cubed x minus 0 cubed, but you don't need to. So x would have to be 0. That's the 0 at that of one of the zeros of the function. And x minus 3 quantity square equals 0 when x is 3. That's your other 0. So one real 0 of this function is x equals 0. The other real 0 is x equals 3. So right away, I can come down here to my graph immediately and put 0, 0, and 3, 0. Those are my 2 x-intercepts. Voila. I'm almost done, believe it or not. I know that might be hard to believe, but it's true. All right. Now I have to consider the behavior. That's everything we just worked on. Is this 0 right here, x to the third, does it have an odd or an even multiplicity? Odd, because 3 is odd. So does that mean I'm going to bounce off the x-axis when I hit 0, 0? Or am I going to go through it somehow, either straight through or flattened out somewhere? Am I going to cross or am I going to bounce? I'm going to cross. What about this second 0 at 3? Let's look at its multiplicity. It has a multiplicity of 2. So this one has a multiplicity of 3, and this one has a multiplicity of 2. Even or odd? Is 2 an even multiplicity or not? Even. So all you have to think right now in your head, baby parabola, baby parabola. So at this 0, you're going to bounce across through. Bounce. The y-intercept is 0, 0. And now you have to determine if your graph is even or odd. Because if you know it's even, you just have to draw 1/2 of it and duplicate it. If you know it's odd, you draw 1/2 of it and then you reflect it over the origin. But I'm not going to do that right now because I want to show you what you do with these zeros. You can practice that later for your homework. I know at 0, 0, I'm going to cross through, but because my multiplicity is 3, I'm not going to go straight through like a line. I'm going to flatten out a little bit like x cubed. And since I'm coming from this direction, I only change my sign near my 0, so I flatten out, and now I head up. I did, I went through. I was negative here, now I'm positive. I went through. No, I haven't gotten there yet. So all I know is I go through, all right? So I go through, and I'm heading up. Now you say, wait a minute. I know in the end here I'm going to be heading up, and I still have to come down and meet this 0, negative at 3, 0. I either got to touch it and bounce back up, or I go through. But I can't go through because look, there's my arm. There's nothing else here that's going to determine my change of direction. If I'm going to change direction, it has to happen at a 0. So I know I'm going to end up, and I know I'm going to bounce here, so I'm going to bounce this way. That's how I'm going to bounce. So what do you do in between here? You're going to have a little teeny hill. Do we care how high the hill is? Absolutely not, because this is a quick sketch. So you could make your hill look like that. You can make your hill look like that. You could make your hill look like that. I don't really care. That's not the point. No pun intended. Okay? It's just what do you do near those 2 zeros? You know how your graph ends up and how it begins. So if you wanted to see what this looks like exactly, this is what it looks like exactly. I just threw this in GeoGebra this morning. See? The highest point here, the turning point right here, is around what? It looks like somewhere around 8, between 8 and 9. But you see, all you're trying to get is the general feel. This 0, and then its correlating factor, x take away 3, has to be a square. This 0, which is x minus 0, or x, has to be a cube. You got everything you need now to work on these exercises. I'm not going to go over this and read this to you, but this is a summary of everything we've talked about the multiplicities and the zeros. I put that on that paper for you. Where do you think this would be a great place to copy? On your cheat sheet for your next test. Put cheat sheet. Cheat sheet, cheat sheet, cheat sheet. All right? Please skip number 1. I want you to, before you leave, I want to make sure you can do number 2 and number 3. Okay, number 2 and number 3 before you leave, as a minimum. There's lots on here to do. In fact, I would save 1 because really 4 and 5 is continuing graphing, and I want to make sure you can graph these things before you leave today.